The following video is the final submission in the America Makes Geothermal Prize. This is Team Plugs, and the title of our presentation is Additively Manufactured Gas Sparger for Gasless Geothermal Technologies. Our technology is focused on developing a new pumping technology to reach hotter and deeper geothermal fluids. Our team is made up of researchers from WVU and industrial experts in the geothermal industry. We also partner with Oak Ridge National Lab, National Energy Technology Lab, and Exometry to print our parts, and we have identified the Utah Forge project as a potential test site for the project. Airlift technology is an alternative pumping method for geothermal wells. It involves injecting air within the well, allowing the air to rise, imparting momentum and displacing the geothermal fluids towards the surface. For this pumping strategy to be competitive, the efficiency of the overall process needs to be improved. Airlift technology has several advantages over line shaft pumps and electrical submersible pumps, which are typically used in geothermal wells. Those advantages include ease of maintenance, deeper access to geothermal fluids, and no moving parts. The focus of this project is on the sparger. To have efficient operation of the airlift technology, it's necessary to optimize the sparger for a given well condition. This includes the depth of the well and the required flow rate of the well. To optimize the sparger, both the internal and external geometries of the sparger need to be optimized. Because each sparger has to be optimized for a given well, it makes it a good candidate for an additive manufacturing approach. In this project, we have elected to use a direct metal laser sintering approach of stainless 316 for our sparger design. The image on the right is a photo of the 3D printed sparger. This sparger has a threaded connection for a gas valve, which will open and close to allow gas into the sparger. There's also an internal passage that you can see in the left figure that is a manifold that distributes the air to the orifices. This 3D printed part is integrated with a side mandrel by sectioning the side mandrel and welding in the 3D printed part. This is shown in the leftmost photo of the gas valve AM sparger integrated with the side mandrel. The right side mandrel is the one that's available in the oil and gas industry. By integrating our part with the oil and gas side mandrel, we're able to increase the efficiency by 20%, and we're also able to quickly deploy this into geothermal wells by building off existing technologies. The following video is a demonstration of the functional prototype in the WVU test rig. The test rig was used to optimize the design of different spargers that were computationally derived. Air is supplied to the wellhead, and air passes down through the annular section to the sparger, where it's injected through the orifices and the mixture is allowed to rise in the center pipe. There's a packer placed at the end of the sparger to allow pressures higher than the hydrostatic pressure to be injected into the well. In actual geothermal applications, there will be multiple stages of spargers with a gas valve attached to each sparger to allow unloading the system or starting the system by sequentially opening the valves. During the testing phase of the project, we received a letter of commitment from Utah Forge well, in addition to 3 other lower temperature geothermal wells. We planned a two-prong approach where we plan to run in the lower temperature Irwin Ranch well while we wait for the Utah Forge well to be drilled in early 2023. By running in the lower temperature well, we can quickly validate the performance of the sparger at greater depths before testing our production environment at the Utah Forge well. If you're interested in our technology, we'll be at the Geothermal Rising Conference between August 28th and 31st.